two comparison tests for series for determining if they're convergent or divergent. The first of those is the direct comparison test. Now, these should remind you of the direct and limit comparison test we had for integrals, and that's because they are very, very similar. We're just applying this now to series. So let's start by defining the direct comparison test. Let the series an, bn be two series such that an is greater than or equal to 0 and bn is greater than or equal to an for all n. So notice we have the series, we were discussing the sequences being the inequalities here. Then, if we know that bn, the larger of the two sequences, converges, if we know that the series bn converges, so too does the series an. And if the smaller of the two sequences, an, if that diverges, if the series of that diverges, then so too does the series bn. So very, very similar to our direct comparison test for integrals. The bigger thing is convergent, so does the smaller thing. If the smaller thing diverges, so does the bigger thing. Now, we do need to show conditions to be able to apply these, just like we did for our integral test. So the condition we have is that both the series that we start with, and the one we're comparing to, that both of those things are greater than 0. So that's not real hard to show. Let's start with an example. Let's determine if the following series converges or diverges. So we have the series from n equals 1 to infinity of 3 times, in parentheses, 1 over 2 plus n all to the n power. And so if we look at this, hopefully what's standing out to us is this looks very, very near to our geometric series. If we didn't have that n there, we would have a geometric series. And so when we're doing these comparisons, we want to compare to things that we already know. That's the easiest thing to do. And so the things that we know very quickly, very easily, we have the geometric series. We also have the p series, one of which is the harmonic series, so just a special series. And so if we can compare to one of those two series, our life will be very, very easy. So I should note too that the direct and limit comparison test, we haven't talked about limit yet, oftentimes can be used kind of interchangeably. Sometimes one may be significantly easier than the other, but we do kind of have some options there. And the other thing I'll say is a lot of times they can be used interchangeably with the integral comparison test, and that should make sense because if we had a direct and limit comparison for integrals, well, if we apply an integral test to a series, well, then we still have a direct and limit comparison test. Now, the challenge there is just sometimes we don't want to do the integral. So in this case, though, I'm going to apply the direct comparison test to get practice with that. So like I was saying, if we had 3 times 1 over 2 to the n, that would be a sequence. A series that is the geometric series. If I think about this particular sequence, 3 times 1 over 2 plus n to the n, well, clearly that has to be greater than 0. And we know that because n is 1 to infinity, it's always positive. We have positive to 2, it's always positive. Raise it to a power, it's still positive. Multiply, it's still positive. I would really like to be able to compare it to 3 times 1 over 2 to the n. That would just be a nice simple geometric series. And let's think about if that's possible. Well, if we're adding something to the denominator, that makes the fraction as a whole smaller. Think about why that would be true. Let me just do some scratch work over here. If I have 2 plus n, well, obviously that is greater than 2. For n, 1 to infinity, this is obviously true. If we add something to 2, it's greater than 2. So then remember, once we take the reciprocal of that, it flips the inequality sign. Take the reciprocal of both. Flips the inequality sign, so 1 over 2 plus n is less than 1 over 2. And then, of course, if we raise it to a power, that remains true because these things are getting smaller and smaller. And then if we multiply by 3, again, that obviously is true. So we know this inequality is true. And so what we can do now is we can state that we know the series n equals 1 to infinity, 3 times 1 over 2 to the n, is convergent, as it is a geometric series. Since, I'm going to state our inequality here, 0 is less than 3 times 1 over 2 plus n to the n, is less than 3 times 1 over 2 to the n. the larger sequences series converges, so too must our series, summation n equals 1 to infinity of 3 times 1 over 2 plus n to the n by the direct comparison test. And I'm going to abbreviate this DCT. That's a pretty common abbreviation. So this is a complete answer. We have shown the inequality is true. In this case, it wasn't very hard to think about it. I don't actually need to do the scratch work on this one. I think we can all look at this and know this is a true inequality. Showing that it's greater than 0. I've stated what that larger, in this case, we needed the larger series to converge, which it did. And because that converged through the geometric series test, stating how, or through the geometric series, stating how that converges, well, then we know that the smaller sequence, the series for that must converge as well. In sequences here, I'm using the sequences to look at the inequalities, and I'm talking about the convergence and divergence of the series. So do be careful with that language. So again, complete answer, we need to show the conditions are met, state what that larger or smaller one is doing, whichever way we need it to be. If it is divergent, we need the smaller to diverge, state how, and then state the test we're using, in this case, direct comparison test. All right, let's look at another example, example number 2 here. So here we have the series n equals 6 to infinity of 3 over n minus 5. And so I look at this, and just like I did with that last one, I'd really like to be able to compare it to something right away. And I'm doing that before I even show those conditions are met, because I need to know if it's going to converge. When I say need to know, I'm trying to make an educated guess. Because if I know it's going to diverge, or if I think it's going to diverge, I'm going to be looking for something smaller. If I think it's going to converge, I'm going to look for something bigger. So starting off by thinking about what the series is going to do is useful. And a useful way to do that is just kind of ignore the 5 in this case, right? If I just kind of cover that up, this looks very much like the harmonic series. And so we know that the harmonic series diverges, and so what that tells me is I need to show that this is actually the low case. We want to find something between 0 and 3 over n minus 5 to state that it's diverging. So I'd really like to compare to the harmonic series, which is just an n in the denominator. And when we do this, if we make the denominator smaller, it makes fraction as a whole larger, kind of the opposite language we just used. And then if I want to, I could just go ahead and make the numerator 1, because that's even smaller. That's just a basic harmonic series now. And so we have a true inequality. We know it's greater than 0. And we know it's greater than 0 for n is equal to 6 and larger. It wouldn't be true if it was, let's say, 4. 4 minus 5 is a negative, so that would break this. It would be a challenge. The bigger challenge would be n equals 5, because that's a undefined value. So we know this is a true inequality, and so now I just need to state the results. So we know series n equals 6 to infinity of 1 over n is divergent, as it is a harmonic series, because 0 is less than 1 over n, less than 3 over n minus 5. Direct comparison test tells us the series n equals 6 to infinity, 3 over n minus 5 must also diverge. So again, I've compared it, made sure that comparison is true, stated what the thing I'm comparing it to does, in this case it diverges, because it's a harmonic series. We stated that inequality again, and then stated the test that we used to make our final conclusion. This isn't also, I'm not just cleaning that up because that looks terrible. Also, there we go. All right, let's take example 3 here. So example 3, we have a series n equals 1 to infinity of 3 plus sine n to n squared power. And once again, I'm going to use the direct comparison test. So just a second ago, you probably saw what's coming in the next video, limit comparison test. I will say that a lot of these could be either the direct or the limit comparison test. One exception to that, one that direct comparison test is much, much easier on anytime we have these trig functions. And the reason for that is, remember, if we take the limit as n goes to infinity, trig functions bounce up and down, right? They go from -1 to 1, depending on if there's some sort of amplitude, it might be even larger, but they bounce around, so they don't have a clean limit value. And so for that reason, it's really easy to use a direct comparison test when we're adding and subtracting these trig values. Again, the first thing I'm going to do is just kind of make a snap judgment, and I see that n squared in the bottom. If I just kind of ignore the fact that sine of n is just -1 or 1, relatively small value, n squared the driver of this function, so that appears to be a p-series with a p larger than 1. So I'm assuming that this thing is going to converge through the p-series. So what I'd like to do is I'd like to find something larger than this. Well, what we just said, the sine of n is going to at its most be 1. So if I wanted to, I could choose something like 5 to put in the numerator, because if this is at most 1, well, 3 plus 1 would be 4. Well, 5 is clearly larger than that. So I now have a true inequality, and I have something I know converges because of the p-series, p is greater than 1. So we know that the series n equals 1 to infinity of 5 over n squared converges because it's a p-series with p greater than 1. Thus, since we have this inequality, the direct comparison test tells us that the series n equals 1 to infinity, 3 plus sine n over n squared must converge. And there we have it. So those are 3 examples applying our direct comparison test. Now, one thing you might be wondering is, hey, on this one it worked out really nicely to where we could just drop that 5 and it was smaller. And obviously if we had something like an n squared minus 5, well, we would have had a convergent series, and so just dropping the 5 doesn't make it smaller. Or conversely here, we had the n plus 2, but what if we'd been making it smaller? And so that's where it gets a little bit tricky sometimes to say these inequalities. The inequalities are not always so easy as to just drop that constant. In this case, I gave you 3 examples where we could very easily drop it or manipulate that constant like we did in this last case. Not really constant, but manipulate that sine n value to get a true inequality. But what if it's not so easy to get that direct comparison? And that's where we're going with our limit comparison test. Our limit comparison test, in the next video, we're going to see where we don't need to have a true inequality. We can just compare it to something that we know what it does and get to a result. Now the challenge with that is we have to be able to find a limit. And so again, things like trig values can be a little bit more challenging when we do that. And that's where it's nice to have both of these tests. Again, both of these tests could often be used, but sometimes one or the other is much, much easier. So we'll take a look at the limit comparison test in just a minute.